So question 1 is saying it's having two parts, part A and part B. Part A is saying a hot water bottle cools down from 70 degrees Celsius to 15 degrees Celsius, releasing 60 or 650,000 joules of thermal energy. Calculate the mass of the water in the hot water bottle. The specific heat capacity of water is 4,200 joules per kg degree Celsius. The specific heat capacity of water is 4,200 joules per kg degree Celsius. So this question, is it very difficult? Because it's straight to the point. So question 1A, they've given us a water bottle that is cooling from 70 degrees Celsius to 15 degrees Celsius. To 15 degrees Celsius, and by so doing, it's releasing thermal energy Q, which is equal to 650,000 joules of thermal energy. So they want us to find the actual mass of this water. The mass is what we're looking for. And how we're going to calculate our mass, we're just going to use the same principle of the specific heat capacity of this same water, because we know to say the thermal energy that is released or absorbed by a heating element will be equal to the mass of that element multiplied by the specific heat capacity of that element multiplied by the change in temperature that is being experienced. So they've already given us the heat that is being released. They've already given us the change in temperature here. They've already given us the C to say this is 4,200 joules per, per kg degrees Celsius. Let me just check the units again. Okay, joules per kg degrees Celsius. Per kg degrees Celsius, like this. So we're just going to get these values and plug them into this formula and find our mass. So I can rearrange it first so that I make my M the subject of the formula. Let's say divided by T over divided by T multiplied by delta, or divided by C multiplied by delta T, even on the other side divided by C multiplied by delta T. This will cancel out. That means our mass is equal to the thermal energy Q divided by C multiplied by the delta T, which is the change in temperature. So our mass will basically be equal to 650,000 divided by 4,200 multiplied by the change in temperature, which the change in temperature is 70 degrees Celsius minus 15, like that. So this is going to give us how much? This is going to give us 650,000 over 4,200 multiplied by 55, like that. And the final mass of this water will be equal to 2.81 kilograms. The final mass of the water will actually be equal to 2.81 kilograms. So if you've noticed, when we're talking about the change in temperature here, we say it's T final minus T initial. But you might be wondering why I wrote T initial minus T final here. It's because if I was to put it in this way, I was going to get this negative. And this negative doesn't have to confuse you, because this energy that we have here, it's being released. And since it's being released, that means this water is losing energy. So that, which means the energy here is also negative. Here, this energy is also negative. And this negative that we have on our numerator here, and the negative that we are going to have when we use this root here, is going to cancel out, such that we're still going to end up with a positive mass. So in case you had a question on that one, that's how we go about it. Let's go to question B. Question B is saying a tray containing 0.40 kilograms of water at 22 degrees Celsius is placed in a freezer. The temperature of the water drops to 0 degrees Celsius in 10 minutes. The specific heat capacity of water is equal to 4,200 joules per kg Kelvin. Calculate 1, the energy lost by the water as it cools to 0 degrees Celsius, and 2, the average rate at which the water is losing energy in joules per second. Okay, so this is also a question which is straightforward, and it is also talking about specific heat capacity, fortunately. So I'll say my question B. My question 1B, we've been given mass of this substance to be 0.40 kilograms. Then we've been given the specific heat capacity of the water to be 4200 joules per kg Kelvin. So this is actually the same. Whether they give you kg degree Celsius or kg Kelvin, it's the same, because when we're looking at temperature scales, we say the change in temperature in degree Celsius is the same as the change in temperature in Kelvin. So these units actually don't or are not supposed to confuse you very much. Then we've been given the change in temperature to say it's changing from 22 degrees Celsius to 0 degrees Celsius. Then what else? They've also given us time of 10 minutes. If I convert this into seconds, I'll multiply it by 60 to get 600 seconds, like that. Now, they've asked us to find the energy lost. They've asked us to find the energy that is lost by the water as it cools down to 0 degrees Celsius. So how are we going to calculate this energy that is lost? We're going to use the same method that we used in part A, because we know to say the energy lost, Q, is equal to MC change in T, like that. This guy, the Q here, is the one which is going to give us the negative change in energy. Since this substance is cooling down, this value of energy should obviously give us something negative, if I can say, because we're having 0 as the final temperature. So if we say 0 minus 22, we're going to get a negative temperature. But to avoid that, we can also apply it the same way. But in your mind, you should just know, if you've been learning physics by now, you should know that the final temperature or the final change in energy that you're going to get here will actually be negative. So I'm going to say my Q will be equal to the mass of the water, which is 0.40, multiplied by the specific capacity, which is 4200, multiplied by the change in temperature. The change in temperature is 0 minus 22, like this. So this is going to give me 0.40 multiplied by 4200 multiplied by negative 22. Okay, so if I plug this into my calculator, I'm getting my Q as exactly being equal to negative 36.96 joules. So that means the energy that is lost is actually equal to 36.96 joules, or 36,960 joules is the energy that is lost. And since it's being released, it's negative. So that is part 1. And part 2 is asking us to say the average rate at which the water is losing energy. The average rate at which the water is losing energy. So this one is also a very simple question. We've already converted our time into seconds, and we found to say the time taken for this change in temperature to take place is actually 600 seconds. Then, if we have our time, we know to say power, or we know to say energy is equal to power multiplied by change in time. So what are we looking for? We are looking for the rate, of which the rate at which it's losing is the same as the power. So I'm going to say divide both sides by delta T, even the side by delta T. That means my power will be equal to what? Will be equal to Q, which is the energy lost, divided by delta T, like this. So this is equal to the Q that we're using here is the Q that we've already calculated, and we found 36,960 joules divided by the change in time, which is 600 seconds. So that means the rate at which this water is losing energy will actually be equal to 36,960 divided by 600 seconds. If you want, you can put a negative there just to make sure that the power is still negative, or is still acting in a negative way. It's removing energy at this rate that we're about to calculate. But to avoid this confusion, we always apply absolute values here. So that means this negative actually doesn't need to be there, because power is the same. The same way, the same rate it's going to be adding energy is the same rate at which it's going to be removing energy. So that 6,960 joules divided by 600, this is actually going to be equal to 61.6 joules per second. So this is the rate at which the water is losing energy. And that means we are done with question 1. We can move on to the next question, which is question 2. And question 2 is saying a student investigates how the temperature of a 0.20 kilogram lamp of unknown substance varies or varied when it was heated as shown in the figure below. He recorded the temperature until the lamp melted and then boiled. The power output of the heater was constant at 600 watts. Okay, so this is the diagram that we've been given, and this diagram has actually been drawn to scale. So the thing we're supposed to take note of first is the actual scale that we're using to calculate whatever we're going to be calculating from this graph, because everything that we need to answer on question 2 is actually coming from this graph. So we've been given power of 600 here. This is the power supply, and the power supply is constant throughout this process. And question A is saying, what is the latent heat of fusion? So if you check this diagram, the latent heat of fusion is when the temperature is constant, and it is the heat that is being used to convert the ice from its ice state to the liquid state. And when you are doing that, temperature remains constant. And this is the graph which is showing us where latent heat of fusion is actually located. That's where the melting is taking place. The temperature is actually constant at 0 degrees Celsius. Now, if we want to calculate the latent heat of fusion, what are we supposed to find first? We are first supposed to find the thermal energy that is absorbed to convert this ice into liquid water. So we're supposed to calculate the Q. And when we calculate the Q, we know the formula for latent heat to say the Q that is absorbed is equal to what? Is equal to mass multiplied by latent heat of fusion. So if we want to find the latent heat of fusion, we're going to use the mass and the thermal energy that is absorbed, like that. So how are we going to calculate the thermal energy that is absorbed? We are going to use the same approach that we used on question 1B part 2, whereby we're going to say Q is equal to the power supply multiplied by the delta T, like that. And we've been given T in the x-axis, where we've been given temperature in the y-axis. So that means we are able to calculate, or we are able to just get the time from the x-axis, this axis, and plug it into this formula. They've already given us the power supply, this guy. So the only thing we're supposed to find is the time it took to melt this ice. And what time is that? It's the time from this point where the temperature reaches 0 degrees to this point where the temperature starts to rise again. So it is stopping at 100 degrees or at 100 seconds rather. 100 seconds is the final time here. And what is the initial time? If this graph is is drawn to scale, we can see that they haven't given us the beginning time where the temperature is constant. But since we're having these, or it's on a scale of 100, we can tell to say this point is just a quarter of the 100 that we've been given. So we can estimate to say this is actually 25 seconds. That means the time it's taking this object to melt from ice to liquid water is 100 seconds, which is this final second here, minus 25 seconds. So that means it's taking 75 seconds to melt this ice. And I'm going to get this actual value and plug it into our formula in order for us to find the energy that is being absorbed. So I'm going to say question 2. Question 2A. Question 2A, first we're going to calculate Q, and we said Q is equal to what? Q is equal to power multiplied by the delta T. We've said the time that it's taking for the ice to melt is 75 seconds. Then the power, they've said the power supply is constant at 600 watts, which is the same as joules per second, like that. So my Q will be equal to 600 multiplied by 75. Let me just plug this into my calculator. 600 multiplied by 75. This is 45,000 joules. So Q is actually equal to 75,000 joules. And now that we found the power that is being consumed, the power or the thermal energy that is being absorbed, what we're going to do, we're getting this thermal energy and plugging it into this formula. Q is equal to mass multiplied by latent heat of fusion. Divide both sides by mass. That means our latent heat of fusion will be equal to Q, of which Q is 45,000 joules divided by the mass. They've already given us the mass to say it's 0.2 kilograms. 0.20 kilograms. That means the latent heat of fusion is actually equal to what? 0.2. Okay, so I'm getting my answer, which is equal to latent heat of fusion being equal to 225,000 joules per kilogram. So, ladies and gentlemen, that is our latent heat of fusion calculated directly from the graph that we have here. So, our latent heat of fusion is 225,000 joules per kg. Yes. Question B is saying the latent heat of vaporization. The same question is coming again, and we're going to use the same approach as usual. You can tell to say if vaporization is taking place at this point when this liquid water reaches its boiling point, when the temperature remains constant at 100 degrees Celsius. So what are we going to do? We're going to find the power that is absorbed at this point, which will be equal to what? Will be equal to the 600, which is the constant power supply that we've been given, multiplied by the time that this power is being supplied. And what time is that? It's the time from the 200 that we have here, since that's where the temperature is reaching 100 degrees Celsius, to that point there. And that point is in the middle of 700 and 800. So we're going to consider that as 750, which means for part B, our change in time will be equal to what? Will be equal to 750 minus 200, like this, which means our delta T is actually equal to 550 seconds. So if this is the time, we're going to get this time and plug it into this formula to find the power that is supplied. Then we'll plug it into this same formula for latent heat of vaporization to find the actual latent heat of vaporization. So I'm going to say, this is question B now. Question B, we've said time or delta T is equal to 750 minus 200 seconds, which has given us 550 seconds, like this. So we're going to calculate the thermal energy that is absorbed. Q will be equal to power, which is 600 multiplied by 550. 600 multiplied by 550. This is giving me power consumption of 330,000. 330,000 joules. So this is the heat that is absorbed to convert our water from liquid water into gas or into water vapor. So since this is the thermal energy that is absorbed, you're now going to bring the thermal energy that is absorbed when, or the formula for thermal energy that is absorbed when you are converting the state of water from liquid to gas. So this is equal to mass multiplied by the latent heat of vaporization, like this. I'll divide both sides by mass and this side by mass, which means my latent heat of vaporization will be equal to Q, which is 330,000 divided by the mass, which is actually 0.2 kilograms. This is in joules. So that means my latent heat of vaporization will be equal to that guy divided by 0.2. And I'm getting this answer. 650,000 joules per kilogram, like this. So this is the answer that I'm getting, but we can simply write it into its scientific, in scientific notation. So just say one. Let me say 1, 2, 3, 4, 5, 6, like this. So my LV will be equal to 1.65 times 10 to the power 6 joules per kilogram. So, ladies and gentlemen, that is our latent heat of vaporization, 1.65 times 10 to the power 6 joules per kg. That is the latent heat of vaporization. Let's go to the next question, which is question C. And question C is saying the total heat or the total heat energy absorbed when the temperature varied from negative 50 degrees Celsius to the boiling point of water. The total heat energy absorbed when the temperature varied from negative 50 degrees Celsius to the boiling point of water. So this is also a very simple question. Let me just grab some things. They want us to find the total energy absorbed up to this point when the temperature was 100 degrees Celsius, because 100 degrees Celsius is the boiling point of this water. So they want us to find the total energy absorbed up to this point here. Yes, up to that point. So what are we going to do? Anyone who has an idea, what are we going to do in order for us to find the heat absorbed up to that point? We are going to use the same formula, guys. You said in order for us to find thermal energy, we are going to say this is equal to power multiplied by the delta T, which is the time. So thermal energy is equal to the power supply multiplied by the time it takes to reach that particular state. So since here we're only focusing up to the point when the temperature is 200, or the temperature is 100 degrees Celsius. From this point up to that point when it's 100 degrees Celsius, the only time it takes is 200 seconds. And the power supply we've constantly mentioned to say it's constant at 600 watts. So what am I going to do? I'm going to say part C, or question 2C, will be equal to power multiplied by delta T. This will be equal to 600 multiplied by the change in time, which is just 200 seconds. And this is actually going to be equal to what? This is going to be equal to 1.2 times 10 to the power 5 joules. If you have a calculator, you can just try to punch in, see if that answer is the correct one. It's 120,000 joules. 120,000 joules, which is the same as this answer that we've calculated. So, ladies and gentlemen, if we reach that point, that means we've solved all the questions that are on question 2. We've solved all the questions that are on question 2. Now, let's go to the last question, which was question 3 itself. So, question 3, part A is saying, calculate the root mean square speed of oxygen molecules, of an oxygen molecule in the air if the temperature is 10.0 degrees Celsius. The mass of the oxygen molecule is 32.00. I think they wanted to put micrograms. So I don't know what they mean. Or it's ounces. Yes, I think it's ounces. And they've given us the Boltzmann constant as 1.338 times 10 to the power minus 23 joules per Kelvin. And they've given us the conversion factor of an ounce to kilogram. So this is a very simple question, and I posted the video to this topic just today. That's the funny part, on kinetic theory of matter. I posted this video today on my YouTube channel and on the website. I posted it today, just today in the afternoon. So we're going to say question 3A. They want us to find the root mean square speed, which is also known as the Vrms, like this. So the first things first, we've been given temperature of this gas molecule at 10.0 degrees Celsius. So we're supposed to convert this guy into Kelvin. So we're going to add 273.15 such that the new temperature that we're going to get will be equal to 283.15 Kelvin, like that. Then the second thing I'm supposed to find is calculating the mass of one oxygen molecule, or calculating the mass of one molecule. So the mass of oxygen molecule in kilograms will be equal to, we're supposed to convert it, the mass that we've been given, let's convert it into kilograms. So we're going to say 32.00 multiplied by this conversion factor that we've been given, which is 1.66 times 10 to the power minus 27 kgs per ounce, like that. So that means our new mass will be equal to 5. Let me write 5. It's looking like it's a 3. 5.3312 times 10 to the power minus 26 kilograms. This is our new mass. And we're now going to apply this formula, the formula for calculating root mean square speed, to find the root mean square speed of this oxygen molecule. So our V root mean square will be equal to the square root of 3 kb T over M. This is the formula that I even explained in the video that I sent for you today. So this will be equal to what? It will be equal to the square root of, well, let me just write it like this. I'll put 3 multiplied by kb. kb is the Boltzmann constant, and they've already given us the Boltzmann constant in the question. So I'm just going to plug it into this question to say 1.38 times 10 to the power minus 23, and this multiplied by the temperature in Kelvin, and we found the temperature to be 283.15. All this divided by the mass of your oxygen molecule, which is 5.312 multiplied by 10 to the power negative 26. Then all of this is actually under a square root like that. So this will be equal to, I'll calculate the numerators. I multiply 3 by 1.38 times 10 to the power minus 23 multiplied by 283.15. This is actually giving me 1.7 or 1.1712 times 10 to the power minus 20 divided by 5.312 times 10 to the power minus 26. Okay, so if I plug this, I'll just plug them the way it is on my calculator. I'm getting 2.2048 times 10 to the power 5, thereby giving us the root mean square velocity of this guy as 469.56 meters per second. And that, ladies and gentlemen, is the root mean square speed of this particular oxygen molecule. And that is question A. Question B is saying at 30 degrees Celsius and 200 kilopascals, a gas occupies a volume of 20 cubic centimeters. Calculate the new temperature of the gas if 1, the volume is decreased to 10 cubic centimeters at constant pressure, but 2, the pressure is decreased to 100 kilopascals at constant volume. So this one is a very simple question. Why? It's because we're just going to, the only thing you're supposed to know, the only thing you're supposed to memorize, you as a student, you're supposed to know the two forms of the ideal gas equation and the combined gas equation. The combined gas equation is that guy that I also explained about in yesterday when I was teaching the kinetic theory of matter, to say, this is question 3b, part 1. So what you're supposed to know is the combined gas equation. And you know, to say the combined gas equation states to say pressure 1, volume 1 over temperature 1 will be equal to pressure 1, pressure 2, volume 2 over temperature 2. This is as simple as it is. This is the combined gas equation. From this equation, you can derive all the equations that you can talk about. You can derive your Boyle's law from this same equation, the Charles law from this same equation, the Gay-Lussac's law all from this same equation. So you're supposed to know this one. If you know this one, then you're good to go. Because if they tell you to say the pressure is constant, that means you're going to cancel out pressure from this equation. You're going to remain with these two. If they tell you to say the volume is constant, that means you're going to cancel out the volume from this equation and remain with pressure and temperature. If they tell you to say the temperature is constant, that means you're going to cancel out these denominators and you're going to remain with only what is on the top. So that's how simple it is when you actually know this equation. So since they've given us two forms, there's 1 and 2, and they say the equation we're using is, or you're supposed to know, is this one. They've given us initial temperature, T1, at 30 degrees Celsius. Then they've given us initial pressure, P1, at 200 kilopascals. Then they've also given us the initial volume, V1, of 20 cubic centimeters. So what are we going to do first? Let's convert our temperature into Kelvin. I'm going to add 273.15, and this is going to give us 303.15 Kelvin. Then I think that's all we're supposed to convert. Let's now head into into the actual problems that we've been given. So part A, or part 1, sorry, is saying volume decreases at a constant pressure. So which means from this equation, let's cancel out the pressure. That means what equation are we going to use? We're going to use V1 over T1. V1 over T1 is equal to V2 over T2, because they've told us to say it's a constant pressure. We're trying to find the temperature. Yes, we're trying to find the temperature. Its volume is decreased at constant pressure. So which means we're trying to find T2. So let's make T2 the subject to the formula. So we're going to find out that T2 will be equal to T1 multiplied by V2 over V1. And this is actually going to be equal to T1, which is 303.15, multiplied by the second volume, which is 10 cubic centimeters, over the initial volume V1, which is 20 cubic centimeters. And we're going to find the new temperature, T2, as equal to 151.575 Kelvin. So this is the second temperature if the pressure, if the volume is decreased at a constant pressure. The second part is saying if the pressure is decreased at constant volume. So this same equation, they've said volume is constant now, which means we're going to take out volume from this equation. And what are we remaining with? We're remaining with P1 T1. This is part 2. We're remaining with P1 T1 being equal to P2 T2. So we're looking for T2, and we'll make T2 the subject to the formula, which means T2 will be equal to what? T2 will be equal to T1 multiplied by P2 over P1. This is going to be equal to initial temperature, which is 303.15, multiplied by second pressure, which they've told us to say is 200 kilopascals, or rather 100 kilopascals. 200 is the initial pressure. 100 kilopascals over 200 kilopascals. And this is going to give us the new temperature of 151.575 Kelvin. So the temperatures are the same. We're finding the same answer in both scenarios, but that's it. So that's the end of this question paper or this quiz paper.